In this video, what I want to do is further expand our discussion into gas laws. Namely, we're going to focus on the relationship between temperature and volume of a gas, and we're also going to look at the Kelvin temperature scale. But before we do that, what I want to do is a quick demonstration for you. And this demonstration you could do at home actually. It involves a candle, preferably in a glass container like I've got here. This is just normally used to hold our tea bags in our kitchen. And I put the candle in the bottom. It's the only birthday candle I had. I'm much more than 5. I guess the first number matches my age, but I didn't have the second number. So the candle's there, and there's some water in the bottom of this container. Now, what I'm going to do is set that in front of you so you can see what I've got. I'm going to light the candle with my barbecue lighter, like so. And of course, the flame burns because there's a fuel there. This demo is actually more about the volume of air around the candle and the water level. That's what I want you to focus on. So there's a bit of water in the bottom of this container, not a lot. And I'm also going to use just a cup from the kitchen, and I'm going to carefully place it over top of my birthday candle. And what I want you to do is look at the level of the water and also the candle itself. So here we go. So we're placing it over top. And of course you can see that the candle's burning for a second here. Obviously, as it burns out, it was quite dramatic actually. The water level went up a couple centimeters. And that's the whole gist of Charles' law that I would like to talk to you about. Well, in reality, if you look at that system, the volume of air that we see above this candle heated up with the candle burning, but when the candle went out, the temperature of that air that was enclosed underneath this cup cooled down. And as it cooled down, it actually contracted, just like we discussed previously. So that drew up some of the water from the container below to replace the volume of the gas as it cooled. So that is a very simple demonstration that shows that volumes of gases go down as you cool them down, and of course they expand as you heat them up. Now let's go to some more serious chemistry here. So we're going to look at the Kelvin temperature scale and Charles' law. Well, we're going to go through an imagination type experiment where if you had 3 different gases at quite high temperatures, maybe as high as 300 degrees Celsius, and you cooled them down and you recorded their temperatures along with their volumes as you cool them down. So on the x-axis we have temperature, on a y-axis we have volume, which might be measured in milliliters. As we cool these gases down, it makes sense that their volumes will drop, kind of like my candle experiment that we just did. If we extrapolate back to a point which we can't reach in the real world, then we can determine that the volumes of those gases all converge to a certain point. And that point, my friends, is 0. When you look at this graph, that point right there represents the temperature at which each of these gases would have 0 volume. And that's a very strange number to comprehend. That is called absolute zero, and it's a mathematical number that again we haven't been able to quite reach within the science experiment realm. It's a theoretical number. So we're going to call that absolute zero. That's equal to 0 kelvins. And we're going to talk about the Kelvin temperature scale. There's no such thing as a degree Kelvin. we simply say kelvins. The good news is the interval size for a degree Celsius and a Kelvin temperature is the same. So it just happens to be when we read this graph that 0 kelvins is minus 273.15 degrees Celsius. We'll just round that to negative 273. At absolute zero, an ideal gas, and that's a gas that behaves well with other gases, the molecules in that gas would have no kinetic energy and therefore would have no volume. And it's a hard number to wrap our heads around, but if we were sitting in a classroom and we were able to cool that room down to absolute zero, leaving the outside warm, believe it or not, the walls would implode, the ceiling would come down, and in theory, we would die, but that room would more importantly have a volume of 0. So very interesting number to think about. Now, we need to be able to convert between Celsius and Kelvin routinely in this unit. So this is a good way to remember it. When you're going from Celsius to Kelvin, we simply add 273, and when we go from kelvins back to degrees Celsius, we subtract 273. Here are some very common numbers that we encounter in the lab. Of course, the freezing point of water at 1 atmosphere of pressure is 0 degrees Celsius, and of course that would be 273 because we simply add 273 to 0. 25 degrees, which we tend to refer to as standard ambient temperature, that's pretty warm. That would end up being a little more than 273. If we add 25 to 273, we come up with 298 kelvins. On the other hand, if we go the other way, 50 kelvins, which is really cold, is a very small number. In fact, it's so small, it's negative. So that would be minus 223 degrees Celsius, because if we subtract 273 from 50, that puts us into the negative range. Very cold. Finally, what we've talked about here relates to Charles' law, and Charles was actually a French scientist who developed weather balloons, air balloons, many years ago, hundreds of years ago, to be honest, and he did studies on gases that were at constant pressure, and he basically verified what we've already talked about. For a fixed mass of an ideal gas, which is at constant pressure, the volume is proportional to the Kelvin temperature, i.e., the volume is proportional to temperature. As one goes up, the other goes up. As one goes down, the other goes down. Well, this was already apparent in our graph, wasn't it? They are proportional to each other, and that is the simple definition of Charles' law.